Okay, so on example 5, I gave you this information, but I'm giving it to you formally right now. Whenever we're doing this limit process to find the area under the curve, we are going to be using rectangles, but we're going to do an infinite amount of them so we can find the exact area under there. So I hope you all know that if we take the width times the length, that's going to be the area of every rectangle we do. So we're going to want to get the width of each rectangle, which we've already said the width is always going to be b minus a over n, because that's your change, that's the change in the width of any triangle, and the b and the a are your intervals. And then right here, the length is going to be the height of each rectangle. So like if I came down here to this picture right here, we're talking that we got rectangles inside this picture where the width down here is b minus a over n, and then this thing over here is the height. This is the height or the length, which are these two things. Now, if you have a right-sided endpoint or a left-sided endpoint, you have to use different formulas. And we talked about this yesterday, and it's in the notes. Whenever you do left-sided, you got to take I minus 1 to get the height, because the first I you plug in is always 1. And when you're going from the left, you're starting at 0 when you're doing your rectangles. So that's why it's I minus 1. So whenever you have a choice, you never want to do this one because it is way more complicated. You always want to do the left one because you only have just regular old I. I said left, I meant right. We want to do the right one, but you got regular old I because we're doing it out to the right and going backwards, kind of. So our width here on this problem, well, they actually gave us all we need. This thing right here is our width. That deal right there is our width. They're giving us that it's a 2 over n width. And then this part in here is our length, our f of this. This is the whole f of this, because you see that little square there? That means they've already done this. In other words, on this particular problem, the x part, the length part, is squared already. That square right there is why there's a square right here. Okay, that square right there. So they plugged this in for my x. This is my x value in here. So maybe I should have said the x part is that and the squared part's that. So I'm supposed to take this and I want to find the limit as n goes to infinity, which means an infinite amount of rectangles, of the summation of this index I equals 1 to n of this function. Now since I is my index, everything that's not an I is a constant. So n is a constant in this problem. So the first thing you want to do is you want to take this 2 over n, my width, and we're going to move that to the, actually we want to keep the limit out here because the limit does affect n. But we want to move the n over, or 2 over n to the front of the sigma notation, because that is a constant. And then I want to square this thing right here. So when I want to square this, it is easier to make this into a common denominator and put it as one term. So I would multiply 1 by n over n to get a common denominator here. So this part right here would end up being n plus 2i all over n squared. And now I'm going to square this thing right here. So I hope I have enough room to get all this on here, because these are a pain in the rear. I should actually have a bracket here and a bracket here, because that n goes to this infinity is going to everything here. All right, so I'm going to square n plus 2i, and if you remember, there is a shortcut to doing a binomial square. So you're going to square the first term, then you're going to take the first term times the second term times 2, and then you're going to square the last term. And then on the denominator, you're going to square n. So I am going to be simplifying this thing down as we go here. So this n squared on the bottom, I can take it out front with this 2 over n, but I want to leave this n squared here because this is a constant, and I'd have to do the summation for the numerator part. So I'm going to rewrite this as the limit and then approaches infinity for 2 over n cubed. And now I'm going to do my rules. Now, I'm going to kind of ignore this part and go ahead and do my next step for this. This is a constant, right? We're doing the summation from 1 to n of n squared, and n squared is a constant. So I'm going back over here to these things, down here at the bottom. And this is the constant rule. The constant rule says you take the constant times the top n. So I'm going to take the c times the n on this first part. So my constant is the n squared. I'm going to take that times n. So when I take that n times n squared, that's going to give me n cubed. Okay, and then I got this constant 4ni. What I'm actually doing here is I'm taking this summation thing and I'm doing each part individually. Okay, I'm going to do the summation of each one of these numerators individually. I'm doing this property again, that's way over here on the front page. I'm doing this property right here, except I got 3 terms, not 2. Okay, so I'm not going to write it down with 3 different ones. I'm just going to do each one individually. And then I also want to show you that this term has an I with it, right? 4n is my constant. Maybe I should write them down individually. But my 4n is going to stay in front, and I'm going to do the summation of I. Well, going back over here to this first page, we have a formula for the summation of I, and it's this one right here. So in place of this part, I'm going to put this in. I'm going to come back over here and put n times n plus 1 over 2n. So this is going to have an n times n plus 1 over 2. Okay, that is the I, the summation of I. And then out here, I got this plus 4. Need this anymore. I don't know why I put a fraction bar there. Then I got this plus 4, and I'm doing the summation of I squared. And again, we have a formula for I squared. We got all the way up to I cubed. But the I squared one is this, so we're going to plug this in for the summation of I squared. So we're going to have n times n plus 1 times 2n plus 1 all over 6. Probably should write this a little better, bigger. N times n plus 1 all over 2. All right, so we're getting closer. Now we want to get and multiply stuff together, and we're going to get common denominators. So this, again, this is monotonous. And that's one of the reasons I want you to see it, because it's difficult to do because it's got a ton of algebra in it. So I got 2 over n cubed out here. And if you look, my common denominator is going to be a 6, right? So I'm going to multiply this first term by 6 over 6 to get a common denominator there. And I'm going to multiply this one by 3 over 3 to get 6 down here. And this one's already got 6. So when I have this thing, I've got 6n cubed right there, plus I'm going to have a 6 underneath all of this thing. Okay? Now I got to do some foiling here. So I'm going to take n times n plus 1. I'm going to kind of cheat and do a couple steps at once. And then I got to take this 4n times both of those. So that's going to be 4n cubed plus 4n squared. What?
Times 3.
Oh, times 3. So we got 12. This one's 12 and this one's 12. Thank you for straightening that out, because it makes a difference in the end. And over here, we've already got the common denominator 6, so I'm going to FOIL these two together first, which is 2n squared, and n times 1 is n, and 2n times 1 is 2n, and 1 times 1 is 1, and these two go together to give me 3n, and then I got to distribute 4n to these. So 4 times 2n squared is going to be 8n cubed, and 4n times 3n is going to be 12n squared. These really don't matter. And 4n times 1 is going to be 4n. We're getting close to done finally. Last, we got to add our like terms. So I got the limit as n approaches infinity, and I still got this 2 over n cubed out front. And I got to add like terms. So 6n cubed plus 12n cubed plus 8n cubed, I believe, is 26n cubed. And I really don't need the rest of it. I'm going to go ahead and write it down, but I need the biggest power is what I need. 12n squared and 12n squared is 24n squared. And then I got a 4n. All over 6. So then I'm going to go ahead and multiply the 2 by everything. That's going to give me 52n cubed plus, and again, this part doesn't matter. Only the biggest power is what matters, if you remember about limits to infinity. So if you look, we're doing the limit of this now, so I only need the biggest powers. That's why I said these don't really count. You see these powers are the same? So when the powers are the same, this goes to the coefficients. Let's see, both those are divisible by 2. So the area under this curve would be 26/3. Now I know the pain in the rear. So now you see why I'm not going to do more than one for each class. Yes? That's a good question.